Suppose a manager of a die-making business got tired of making regular, six-sided dice. He wants to create a die that no one has ever dreamed of making, an infinite-sided die. After years of experimentation and production, he finally came up with one such die. He made it so that the outcomes of the die are the natural numbers. Further, with each roll, we'll get 1 with probability 1/2, 2 with probability 1/4, 3 with probability 1/8, and so on. In general, each outcome omega corresponds to probability 1 over 2 to the omega. In other words, if we were to record the outcomes of many rolls, we would expect on average half of the results to be 1, half of the rest of the results to be 2, half of the rest to be 3, and so on. A manager of a casino saw the potential of this die, and he invested a large fortune in order to buy the exclusive right to use this die. The manager was a greedy businessman, and he doesn't want his investment go to waste. He wants to create a game which on average will bring him infinite amount of money. After years of deliberation and theory crafting, he finally came up with one such game. The rules are simple. In each game, the player rolls the die once. The result, omega, is recorded. At the end of the game, the player gets a predetermined K dollars from the casino. In return, the player must pay the casino 2 to the omega dollars for playing the game. Of course, the player wants the outcome of the die to be as small as possible, so he can earn a positive income. For example, if the constant payment K is set to be $3, and if the player were to play the game many times, he would expect on average to earn $1 in half of the games, in which he rolls 1, and to lose money for the rest of the games. Intuitively, this constant payment K of $3 seems to be too low to attract any player to play the game. The rewards are too little, and the risk is too high. Despite with small probability, one could end up losing a life saving. So what K would make this game a fair game? If the K is too high, the player gets too much money, and the casino would go bankrupt. If the K is too low, the game wouldn't attract enough players. For what K would you be willing to play such a game? Perhaps you can write your estimates or guesses in the comment section below. In order for us to do the following calculations, we need to introduce the concept of expected value. For those of you who are comfortable with this concept, you can use the timestamp in the description to skip to the next part. Expected value is a very useful mathematical tool. More precisely, it is a probabilistic measure of some kind of weighted average of a random variable. To some extent, it captures our intuition about an indefinite value in one fixed estimate. For example, in a coin toss, if we assign value 1 to result of a head and value -1 to result of a tail, then assuming that we have a fair coin, we'll achieve 1 and -1 each with 50% chance. Summing up these weighted values, we see the average value is 0. So suppose we're playing a game where you can bet on the result of the coin toss. You get $1 if the coin lands on the head, and you lose $1 otherwise. Then, you wouldn't expect to win or lose any money on average. Although individually in every single game, you are winning or losing money. The value 0 captures our intuition about the average return of the game. A slightly more involved example is presented here with a fair six-sided die. So suppose we play a similar game in which we're paid a constant amount C, and we have to pay variable amounts omega depending on the result of the die roll. So we pay $1 if we roll a 1, $2 if we roll a 2, and so on. With expected value, we can get a fair value C for such a game, in which neither the host nor the player earns any money on average. We see the only possible results we could have from our die rolls are the natural numbers 1 to 6. Since we assume the die to be fair, we expect each of the result with 1 over 6 probability. Then, to get the expected value of our payments, we simply sum up the weighted averages to get 3.5. This result seems intuitive, because if we set C to be 3, the player loses money if he rolls 4, 5, or 6, and only earns if he rolls 1 or 2. This C favors the host. If we set C to be 4, the player only loses money if he rolls 5 or 6, but earns if he rolls 1 or 2 or 3. This C favors the player. So our intuition matches up with our calculation. 3.5 seems to be a fair constant for C in this game. Looking at our infinite-sided die case, we use expected value to sum up the weighted average of all the values. We see we need to pay 2 with probability 1 over 2, 4 with probability 1 over 4, 8 with probability 1 over 8, and so on. Each side of the die essentially contributes 1 to the amount that the player has to pay. Despite that we roll 10 with close to 1 in 1,000 chance, the fact that we have to pay around $1,000 in this scenario balances the weighted average out. And since the die has infinite sides, the expected value is, well, infinite. Therefore, no matter what K the casino manager set, he would on average earn infinite amount of money. Or does he? A theory versus intuition contradiction here isn't hard to establish. We see with each roll, the player rolls a natural number, which is finite. The payment that he has to make, 2 to that number, must also be finite. Intuitively, average of finite numbers cannot possibly be infinite. This is where our intuitive expectation deviates from our model's mathematical expectation. The mathematical expectation requires us to perform infinite number of experiments, which is neither physically possible to perform nor empirically possible to imagine. We see the average of an infinite series of finite numbers can easily go infinite. For example, if we take the average of the first n natural numbers, as n gets large, the average goes up without bound. However, in reality, no matter how long we spend tabulating this average with this procedure, the average we have accumulated so far is still finite. This is perhaps where our theory departs from our intuition. The greedy casino manager believed in his mathematical calculations, and in order to attract players, he set the K to be 2 to the 20, around $1 million. We see with only probability 1 over 2 to the 20, the manager would earn any income. On the other hand, with probability almost 1, the manager loses. With conditional expectation, we calculate that given the manager didn't win money, he would lose on average more than $1 million, a value that's fairly close to K. Soon, the billion-dollar casino went bankrupt after around 1,000 players played the game. Why? We can easily explain this by calculating the probability that the casino lost every one of the 1,000 games. Assuming each game is independent, we simply multiply the chances. In this case, since the number we're multiplying is way too close to 1, we see the chances of casino losing 1,000 games in a row is still very close to 1. Since the casino is to lose on average $1 million after each game, it isn't surprising that the billion-dollar casino went bankrupt. We see the difference between reality and theory here is that the casino didn't have the foundation to play infinite number of games. This example was to illustrate the fact that the mathematical expected value sometimes deviates from our empirical one, and does not always tell us the full story. Expected value does a pretty good job of capturing our empirical expectation when the random variable is restricted by certain constraints. For example, integrable. But when some of these constraints are broken, the mathematical expectation seems to deviate from our empirical one. As Professor Stephen Shree points out in his book, if we push the model too far, it can depart from reality.